Hi, Professor.
Hello, can you hear me?
Yes, yes, I can hear you. Uh, I think you can see me now.
Okay, I can try and turn on my camera. I don't know. Let's see.
Yeah, yeah, I can see you now. Great,
That's working. Nice.
great, great. Thank you for being here.
Yeah, no problem. No problem. I just saw your email. I was gonna click on, I think you sent a Google Meet before. I was just
Uh,
about to click on that, but then I saw the email, so I clicked on this. So I guess this seems to be work. So we'll do all the meeting in here. Nothing else needs to be.
no, no, nothing
I'll
else.
just share in here.
Yeah, yeah,
So maybe
it's
I should
just
try that.
yes. The fourth one on the top right, the fourth icon is the desktop sharing.
Oh, yeah, yeah. So I may need to restart to share. Let's see. Okay. Yeah, I need to quit and reopen because I need to reset my
Yeah,
settings here.
that's okay.
Uh, no, I've lost the camera. Oh, there's the camera icon. Okay, allow. Good,
Great.
that works. Now let's try one more time for the sharing. Oh, I can. Aha. Okay.
Great. Now we have your
Now let's see. What can you see here? Okay, so
screen.
you see the whole thing.
The whole thing.
Which
Yes.
is fine. Yeah, so then I can just full screen when I do this. I guess
Yeah.
I won't see you, but I can see, but you will be able to see the. I'm gonna
Yeah.
undo that for now.
Okay. Okay.
But yeah, so I won't. So then I don't know if there's a good way for me to be able to see you, and but maybe I don't need to see you.
If you have two monitors, you can put this
Yeah,
screen on two and the other. But if it's
but
going
then
to be hot,
but the other monitor is like over here, like
okay,
so they're like on angles, right? Like one is this way, one is this way.
okay, okay.
So
No problem. I'm
yeah.
here. If someone asks anything in the chat, I'm gonna read it for you. And if anyone wants to talk, I'm gonna give it microphone access. That's
Yeah, that seems completely fine, sir.
great. Great, great. So I think we can start and people will join us one by one. Okay, so welcome everyone. We are so excited to have Professor Amato with us today, and he wants to give us a talk about interesting world of multi-agent RL, and we're very excited to have your talk, Professor.
Thank you very
Okay,
much. Uh,
thank you.
um, so like I was saying before, so I can't see folks, and I prefer if it's more interactive, if people have questions, like I don't mind being interrupted with questions. It's more fun that way, because otherwise I just stare at this screen and I feel like I'm talking to myself, which is not as much fun. So if you have any questions about anything, I would love to hear them at any point. And then, I should keep track of time, but certainly let me know if I'm running over. But overall, so I titled this A Short Introduction to Cooperative Multi-Agent Reinforced Learning. Franz Olehuk and I have a book on decentralized POMDPs, DEC POMDPs. And we did an initial version of a tutorial at Amos 2 weeks ago, I think it was, that was much longer than this. And so this is a shortened version of my part of that tutorial. And we plan on giving versions of this tutorial in the future as well at other conferences like NeurIPS and ICML. So if people have feedback about it, it's great. As I have at the end a link to it, but we're working on a book. I have archived drafts of some parts related to this material, related to cooperative multi-agent reinforced learning. So there's a link to it at the end, and it would be great if anybody has questions about that or feedback. I'd also love to hear that, because we're working on updating that and making that into full book rather than that will be released by a publisher rather than just the archive drafts that we have now. And so starting with that, maybe I would like to know, because there's a lot of stuff here. So but it sounds like people know about reinforcement learning already, and maybe something about multi-agent reinforced learning. Is that right?
Yes, yes. We covered the very basics of the reinforcement learning, multi-agent reinforcement learning in 2 lectures in the class.
Okay, so then later on, when I start giving some overview of stuff, maybe I'll ask, like, do you know about this? Do you know about this? Should I skip this? Should I do this?
Sure, sure, sure.
To get a better sense of what stuff, because there are a bunch of slides here, and I'm happy to go into more detail in some parts that you maybe haven't covered, and then less detail in parts that you have. But overall, the goal here is to give an overview of the background of multi-agent reinforced learning from the cooperative perspective, as well as some of the state-of-the-art methods there. But maybe I don't need to motivate multi-agent systems. Multi-agent systems are especially cool nowadays, although some of them I'm not sure I would call multi-agent systems. But the idea of using agents to coordinate or to compete or to be in the environment is a old problem, but one that is becoming a reality nowadays, right? With everything from drone delivery to fleets of autonomous cars to having multiple home robots, warehouse robots obviously are widely used. This picture from NVIDIA about its future of factories, right, where you have lots of agents in factories, robots, people, computer agents, right, agentic systems, all working together in order to solve those problems. And then nowadays, obviously, there's lots of companies, LLM based agents, right, which people often call agentic systems, right, trying to solve problems for us, right? And we're going to have more and more of these systems that exist in the world. They're going to have to interact with each other, right, whether they're competing with each other, whether they're cooperating, whether they're in a mixed environment. This is going to be a very common thing, especially nowadays, where it's becoming quite easy to create agents, right, and spawn them and put them out into the world. And so we'd like to control these agents, right? And so it's I guess nice to have LLMs that do stuff, but we would like them to do stuff that we want to do, right? So we need to align them or otherwise get our systems to do the things that we would like them to do. And so one of the main ways that we've done that for a while, right, and agents more generally, right, is using reinforcement learning. Right. So here, reinforcement learning for the single agent case has had a lot of successes, right, is becoming widely used. And then there have been some successes in the multi-agent case, right, a bunch of cool papers and demos and these kinds of things, but it's not quite as readily usable as the single agent case. And maybe some of the stuff you covered already. And one of the reasons is because multi-agent RL is quite hard, right? So it's more complicated because there's multiple agents interacting in the environment, and then it's not even clear what multi-agent RL setting makes sense, right? There's a bunch of different settings that you could consider for the multi-agent RL case, right? For instance, you could imagine that you have a bunch of agents that are all centralized, so there's perfect fast communication with each other, right? And you can think of them kind of as like one big agent that's choosing actions together, right, and getting observations together, right? Maybe you want to just be completely centralized in that problem. Or maybe you want to be completely decentralized, right? Maybe you're competitive and you don't want to share information with the other agents, right? And or maybe you can't, right? You don't have any communication with the other agents. So then you only have your own information, and you need to kind of learn in those decentralized settings where only you have your local information, and you have to use that to learn what to do. And nowadays, probably the most common one is actually the third case, which is the centralized training for decentralized execution, or CTDE case, where you assume you have a simulator where you can train the agents in a like centralized fashion, but then you need to execute in a decentralized fashion. So they would only use their own local observation information during execution, but could share information, say, what if you do this? What if I do that kind of thing, right? To try and figure out what to do during execution. And a lot of these cases will also have partial observability, which you've probably talked about to some extent before, and I can talk about here, where agents have some limited view of what's going on in the world, limited communication. There's some limitations in its observation, so it doesn't have the full state of everything that's going on in the world. So the goal here in these slides, all the things that I have in here, which again, I'm happy to kind of skip some things and go into detail on other things, is to talk about the multi-agent cooperative RL problem. So that is the DECPOM DP, and then discuss the state of the art and the different types of cooperative MARL, right? Talk about the centralized training execution case, talk about the decentralized training execution case, the particular algorithms there, right? As well as the CTDE case and the state of the algorithms there, a bunch of which that people may have heard about already or know about already. And then I'll talk about like some of the relationships between these different classes, misconceptions, issues, current methods, and then talk about applications code, future topics, all that kind of stuff. So maybe now is a quick point to stop and ask a little bit more about which particular of these settings that you all have talked about before, or particular algorithms that you've talked about before. Is there stuff here that looks familiar so far? Or?
We only covered the basics of multi-agent RL and just two algorithms, joint Q learning and minimax Q learning. And
Okay,
yeah, just with the introduction to game theory and Nash equilibrium and just these two algorithms.
great. So that's good because that's kind of orthogonal to this issue, right? So then the nice part about the cooperative case is we don't need any game theory. We can just like ignore it because there's we can talk about it in more detail later. There's just one Pareto dominant Nash equilibrium, like so you don't have to. And it's a cooperative problem, so you don't have to do equilibrium selection. You don't have to worry about all the issues that exist in the game theoretic mixed or competitive case. So the cooperative case more naturally follows from the single agent case in that there's you can agree on a joint policy that optimizes the return for all the agents. So we'll get to that, but then yeah, and we'll mention the joint Q learning as well. But that sounds good. All right. So speaking of which, so then this you haven't talked about this model, is that correct?
Yes, yes.
Okay, so this is just the extension, right? So we have maybe I think I have it in a couple slides actually. So we'll do here. We'll start here and then we'll go backwards. So then I don't know exactly the model that you talked about before. Maybe it was a Markov game, which is the fully observable version of this problem. Like the general model problem is this partially observable stochastic game, right? So you have a bunch of different agents that are represented by these little rovers here, right? They all have an action space, right? They take actions in the world, right? They can each get their own set of observations, right? The O's here. And then they each get individual rewards, right? And then in this general case, right, each agent's trying to optimize its own expected return, right, in these cases. But the environment, the updates, the rewards, the observations, all these things depend on the whole set of agents, right? This is the general model problem. So then the cooperative model problem is the subset of this, right? The somewhat simpler case, right? When everything's the same as that POSG case, except for here, there's only one joint reward. So instead of having a different reward potentially for each agent, there's a joint reward that's given to the team. because it's assumed to be a cooperative problem. So there's only one reward that's given for the whole team, right? It doesn't matter which particular agent does it or if they just do it together. As long as the team gets the reward, that's the thing that matters, right? So it's like some of these problems before, like if I have a fleet of autonomous cars, they're all my cars. I don't care which particular car picks up which particular person, right? The whole team gets the reward, right? As long as I clean the floors, right? It doesn't matter which robot does it or deliver an object, right? It's just the whole team gets it. So then that's the general cooperative model problem. And then, so like we talked about, so now it extends from like the single agent case, right? So we're still, there's a single reward. So we're just maximizing that single, the cumulative sum of those rewards over the horizon or the infinite horizon of the problem. And because it's we consider the more general case here, so the partially observable situation, which I'll mention the fully observable situation later on, right? The agents may need histories, right? They may need to remember some information in the past to help them make decisions about what to do, right? When you're in a partially observable environment, right? I haven't, my sensors are limited, so I haven't seen the other robots in 22 time steps. But last time I saw them, they were in a particular location. I may need to remember that to help me figure out what I should do in the future, right? I can kind of infer where they may be based on where I saw them in the past. And if I don't remember that stuff, right, then I won't be able to make those sorts of decisions. So then that's why we represent these policies as mappings from histories, right? And later on, we'll just use a neural net to try and learn some history representation that tries to remember the important stuff as necessary in those cases, right? The maps from those histories to actions, right? And these are decentralized. So that is, each agent has its own policy that only depends on its own information. So that is its own sequence of observations and actions that it's taken, right? And they may see the communication could exist in these models, or they may see the other agents right through their observations, but it's not explicitly modeled. It's just actions and observations in this case. Any questions so far?
There is no question, Professor.
Okay. All right. So then I'll talk about the different cases, right? So then now there's this. Oh, go ahead. Yeah.
Ask, okay, I'm gonna give him access.
Hello, can you hear me?
Yes.
Thank you, Professor. My question is not necessarily related to your current slide, but I wanted to ask you if you, in multi-agent environments, sometimes when agents are many, possibly infinite agents, uh, we analyze them in the context of mean field games because it's
Yeah.
just too complex to model every individual agent. So I just
Mhm.
wanted to ask you, if possible, you can also give your insights along your presentation about mean field games or how we can apply these state of the art methods to the environments where we have many, possibly infinite number of agents. Thank you.
Oh, that's a good question. Yeah. So yeah, all this stuff. Yeah. So I think I can maybe say more at the end, but I'll say right now, yeah. So those are the objective is very different in those cases. Some of the things are related, but those fields don't talk as much as they should. I don't talk as much to the mean field people as I should, and I don't read as much of the mean field stuff as I should. So maybe there's stuff that I should be aware of that I'm not. But some of the ideas can be applied in the mean field case, but other things break. So it's, I think, a bit complicated. But again, I'm happy to talk about it more later on. Um, any other questions now?
Not yet.
Okay.
Okay, I think it's fine.
Yeah. Go ahead.
Yeah, there is no question.
Okay. So then I'll jump to the different settings, right? The centralized setting, the decentralized setting, and the CTDE setting. The centralized setting is maybe the least interesting to some degree. because it's basically, so the assumption in the centralized setting is that you just have a centralized controller, right? So you basically think of the agents as just one big agent, right? And that one big agent is just kind of factored across the particular underlying agents, right? So the centralized agent takes in the joint action, right, or chooses the joint action, sees the joint observation, right, the observation of all the agents, right, and then chooses the particular action, right, that the agent should take, right? And then I kind of separate the agent and a controller algorithm a little bit, because during optimization, right, you see the rewards, but during execution, you don't see the rewards. So you often have, you know, an algorithm that's looking at the rewards and optimizing, like choosing what the agent should do, right, and then you just execute that policy, you know, on the agents to that, right? So, and I will state that this is not a DECPOM-DP, right? So I'll have in the next slide the particular models that we have there. The DECPOM-DP assumes that you have decentralized execution by the different agents, but in this case, we assume we have centralized execution, right? So that all the information goes to like one centralized controller, right? And that centralized controller spits out all the actions for the agents. And because it's represented that way, right? So now we can model it. The common way of modeling a centralized problem is it as an MPOMDP or an MMDP, multi-agent POMDP or a multi-agent MDP, right? And then it's basically, it looks very similar to what we had in the decentralized POMDP case, but the difference is the policy representation. So the policy representation here is represented as you take in the joint history, right? So it's a mapping from the joint history, so that histories of all the agents, right, to the actions for all the agents, right? So you get to control, you get to condition the actions of the agents on the other histories of the other agents, right? Which is what you can't do in the decentralized case, because you don't have that information in the decentralized case, right? And this is the parse observable case, and then you can do the same thing, right? It's a common model, the MMDP in the fully observable case, right, where the agents get to see the actual state, right, and choose actions based on the state. And there, you don't need to remember history. You can just have mappings from the state to the actions of the different agents, right, to solve the problem. And then, so this is what your joint Q-learning would be. It's kind of a DQN version of it with a recurrent layer, so it makes it DRQN. But this is joint Q-learning, right? So we have Q-learning, which you already know about, right? And I assume you already know about DQN as well. So then it's our deep version of Q-learning, right? Where we feed in maybe some higher dimensional representation of the state, right? Like an image, right? And we get output that is the Q values for all the actions at that particular state. So we can argmax over to choose the action, right? And then because it's parse observable, like a simple thing that you could do is you could add a recurrent layer to your, or some number of recurrent layers to your network, right? And now we have deep recurrent Q networks, or DRQN. So then we have these DRQN agents, and now we can do this for the multi-agent case. In the centralized case, we just make that just a big joint action, right? So then we feed in the observation of the agents, right? All the agents in that case, right? And then we get the joint action, right, for all the agents out at the other end. So it's just like a big single agent version of the problem. And we can do that not just for DRQN, right? But we can do that for any method, right? So you could take any single agent method, right? And then if it's a centralized multi-agent method, you can feed it in all the agents' observations, right? And then get use a recurrent network if it's parse observable, right? And then get output of all the agent actions at the other end, right? So then this is a thing that you can do, right? But it doesn't scale very well, right? Because as the number of agents gets larger, it doesn't have to be infinite like the mean field case even, but if it just gets reasonably large, if you have 10 agents or anything along those lines, right, then this action space is going to get huge. The observation is going to get huge. It's going to be difficult to solve these large problems. It also only works in these cases where you can send all that information, right, to some centralized controller and get that information from the centralized controller. So it doesn't scale super well in terms of the agents. But there are a bunch of methods that try to deal with the multi-agentness of these problems to try and make it more scalable, such as using coordination graphs, where you assume like it's not completely all the agents aren't completely dependent on each other. Just some agents are dependent on other agents, right? There's subsets of agents, and they could be overlapping with each other, right? So that you can do more efficient operations, like the argmax you can do more efficiently rather than argmax over the full joint space, right? So you can use things like coordination graphs. And there are famous cases like Alpha Star where there's lots of things that you can do to try and make this more scalable, but still solve it in a kind of centralized approach. So it's certainly still is used. It's just not it's not the main topic that I'm going to talk about here. It's not as active of an area of research as the CTDE case, for instance. I'll also say that, so this is kind of assuming that you have centralized information and centralized control is the stuff that I've talked about so far, where you just have that centralized controller that's taking in the information for all the agents and spitting out all the actions for all the agents. But you can actually decentralize that. So the MMDP model and the MPOMDP model are just models, but then there's a bunch of papers that think about the centralized control of them, and there's papers that think about the decentralized control of them. So you can actually decentralize the solutions to MMDP and MPOMDP. That is, once you solve them using the methods that we talked about before, you can break up the actions, right? So for instance, in the MMDP case, for the fully observable case, once you have this mapping, right, from states to actions for all the agents, you can just, for each agent, you just give them their part of it, right? So each agent can have their part, which is just their own mapping from states to their particular action they would take in that state, right? So for all the different states of the world, right? Similarly, in the MPOMDP case, because the agents are allowed to condition on the histories of all the other agents, you would just do the same thing. You'd give the agent their part of that policy, and they could just execute their part. So again, once you've solved the problem, the centralized version of the problem, because the information is centralized, you can decentralize the control aspect of it. But that's not true for the DECPOMDP case, right? So once you have a centralized solution, you can't decentralize the information part of it, right? So if my action already depends on your histories, I don't know how to get an action when I don't have your histories anymore, right? So that is, when I only have these local histories, HI, I don't know how to take a centralized solution and turn it into a decentralized solution from that respect, which, yeah, we can talk about more later on as well. Okay, so that's the centralized case, a quick kind of view of the centralized case. I was also going to do a relatively quick view. The decentralized case is more studied. There's more stuff there. And then I'll talk more about the CTDE case. Again, maybe I'll stop real quick to ask if there's any questions so far. Okay, I take that as a no, but again, I'm more than happy to be interrupted.
There's no question. There's no question.
Okay, yeah, go ahead.
There's no question. No.
Oh, there's no questions.
Oh, sorry.
Yeah, no problem. All right, so the decentralized case. So now the decentralized case is the opposite of the centralized case, maybe obviously, right? Where the assumption here is that each agent is learning completely on its own, right? So then it observes its own observation, OI, right? Takes its own action, AI, right? And then at a resulting history, HI, right? And then you have a decentralized algorithm controller, right? That sees that information, right? As well as the reward and optimizes what to do. Right. So here, this is the case where if you are completely learning online, right, you don't have a offline coordination phase where you can try and learn, right, and you need to execute in a decentralized way. This is what you would have to do, right? So in many methods that are not cooperative, right, you would also have to do that in that case too, because you're not sharing information, you're not allowing yourself to have this coordination phase. Right, so then you would have to do decentralized learning in this case, right? So that's this is a reasonable problem to solve. Like, there's a lot of problems that you would have to solve in this sort of way, and it also makes it more scalable because unlike the centralized case where we had the joint information, right now having the local information, right now we just have local action spaces which are much smaller, local observation spaces which are much smaller. The problem here, though, is that the problem becomes non-stationary because if the other agents are learning, right, like you in this picture here, we imagine it's just a single agent problem where I'm just learning from my own action space and my own observation space. But the other agents, I consider them part of the environment. They're changing, right? So then from my perspective, the environment's changing over time as those other agents are changing their policies. So that makes the problem non-stationary, right? It changes over time. So then it may make my learning unstable and not be able to converge. So, but there are many methods that try to deal with some of these issues, and we can talk about that in a second. Starting from the action value case, right, the queue-based methods, some of which you may have talked about before, but these are basically starting out with just applying, again, single agent methods, right, to this multi-agent case, right? So I won't go through this in detail. It's just queue learning, but it's queue learning just assuming that I just have my own information, right? So then it's like queue learning for the parse observable case, so we have histories, right? But otherwise, I'm just taking my own actions, right? Seeing my own observations, right? Acting in the world and doing queue learning based on that information, right? That's it. The kind of tricky part that's kind of hidden here is that even though I'm trying to just apply a single agent method in a multi-agent environment, whenever an agent takes an action in the world doesn't only depend on that one agent, right? The observation distribution, the transition distribution, the rewards depend on what actions the other agents took and what observations they saw, right? So even though I'm in my algorithm, I'm kind of ignoring all that stuff still has to happen in the background, right? At every time step, all the agents take some action, right? And see some observation, and then the next time step happens, right? So even though this algorithm doesn't list those actions and observations from the other agents, they're still kind of happening in the background in order to generate all this stuff. Then there are papers that try to analyze what happens in this case, right? So this is, again, where the non-stationarity comes from, is if those other agents are changing over time, the problem becomes non-stationary. If those agents are fixed, then you can imagine that you're just learning in some POMDP where those other agents are part of the environment. So it's not non-stationary because those agents aren't changing. If that's the case, then you learn in this particular POMDP, which again, I'm happy to go into detail, but maybe I'll skip it in terms of time. So then you can think about like what's really happening in these problems, and there are methods that try to deal with this non-stationarity from this kind of perspective, which we can talk about in a minute. But first, like what happens now in these cases, right? So then if we just do this, right, if we do some form of IQL, it may not converge, right? So it may diverge, right? So we may not be able to get any solution to our problem. And in more generally, convergence properties of Q-learning-based methods in decentralized POMDP is an open question. When will they converge? When they won't, right? What properties you need for them to converge? What they will converge to? It's an open question. So there's lots of if you're bored and you want a topic, that's a probably hard but interesting topic to think about. And then IQL like is still commonly used, but it's as a baseline, but it performs poorly. Oh, and so I'll also say that there's also this issue. So with a Q-based method, right, or a value-based method, so you learn the value function, but then in a decentralized situation, it may even be hard to coordinate because maybe there's two values that are equally good, right? And now I don't know which one to pick, and there could be a miscoordination, right? One agent would pick the highest Q value, one action that has the highest Q value, and then another agent would pick another action, right? And then the joint Q value may be lower. So I'm going through that example super quickly because of time, but I can, if it's unclear, I can go back and talk about it in more detail. So then obviously we can extend these ideas to the deep case, right? That was the tabular case. People have extended DQN or IQL to the deep case. So this is the case for using DRQN applied to each agent, but otherwise it's basically the same thing. There's just a couple of other things that wind up popping up as a result, right? So now we have this non-stationarity issue, convergence issues that we had before. We also have this additional issue that comes up, which is the buffer. So then the original versions, right? So DQN, as you, I think, know, right? So you populate a replay buffer, right? Which you then draw data from to try and learn. So now original versions of IQL for the deep case here, would just populate each agent's buffer separately. So agents then would draw data from their buffers separately, and they would learn from different data. And that also made it unstable and difficult to learn. So then later versions, such as this method, solve that problem by trying to coordinate on their buffer selection, right? So then in the centralized case, you can imagine, and some methods do this, right? You can just create a joint buffer, right? Throw all the data into the same buffer, right? And then draw from that together, right? Just like you would like in regular Q-learning. If you're doing online learning, you're learning from the same data, you're updating from the same data. But if you're doing IQL and generating buffers separately for the DRQN case, the IDRQN case, right? Then each agent will have different data that it's pulling from its buffer. So one of the contributions here in this decentralized model method, where the names are getting a little bit cumbersome, is DEC H DRQN. One of the ideas was to try and coordinate on the buffers. There's other contributions. They also did multitask stuff, which I'm not talking about here. And there's hysteresis for trying to be optimistic to deal with multi-agentness, right, of exploration. So one of the non-stationarity issues is other agents explore, and it makes it so that it's also harder to learn in that case too. So hysteresis is one way of being optimistic and trying to learn from better returns as well. I'm going through this stuff quickly based on time, but again, I'm happy to go through any of it more detail if you'd like. But then this is the idea of the concurrent learning. So then again, the idea is that you want to have a joint buffer for all the agents, but in the decentralized case, you can't have a joint buffer for the agents. So that the real idea here is to just then instead have to label your buffer with the particular episode and the index in the episode, and then have coordinate on random seeds. So that when you pull from your buffers, even though you have different buffers per agent, right, then you pull from the same place in the buffer, right? The same episode, the same place in the episode when you're training your DRQN method. So that's the basic idea. So in this concurrent learning idea is super important for all the methods and getting them to work well. And it kind of happens naturally in the policy gradient methods, but then you have to do these little tricks in the Q-based methods in order to get them to work well. And then there's a bunch of other methods that have been extended, right? So lenient learning, likelihood Q-learning that I won't really have time to go into. It hasn't been as active an area, again, as CTDE, but still widely used. Policy gradient methods are more used probably than methods like IQL. And building on the original method from 2000, decentralized reinforce. The ideas are basically, like we said before, it's just applying a single agent method to a multi-agent context. So it's just extending reinforce to this multi-agent context. And this is, again, extended to the parse observable multi-agent context here. So if you know about reinforce, then this should be pretty familiar here. But then, so reinforce, it's Monte Carlo, so there's no value model here in this case. We learn a policy, and we have a parameterized policy. The nice part about this, though, is so we're learning on policy, right? So then we don't have that issue of non-concurrent learning, of pulling differently from the buffers. And as a result of that and some other nice properties, this can actually be proven to converge, right? It may not converge to a global optimal solution, but it's proven to converge to the same solution that you would get if you use a centralized method, right? So then Peshkin et al. Prove that you can decentralize the centralized policy gradient. So then you could basically factor it into the different agents, like we did in that how you decentralize a solution once you generate the centralized solution for it. So we can decentralize the gradient in this case and give each agent its part of the gradient, and it winds up being the same as what you would get if you just directly calculate the gradient, each agent on their own. So this does have nice convergence guarantees, unlike the Q case, which is nice, assuming concurrent learning and some other assumptions like that. And then you can build on that. You can then add a critic model there. So now you have a value model in that case. Otherwise, this is the same. But then it retains the nice properties. So now this would also converge to a nice local optimum, at least. And you can do that for any single agent method, right? So again, you take any policy gradient method. So for instance, IPPO, it's a common thing to do. And then you can now build on these other methods with any single agent method, extend them to this case in this way, right? And then some of the guarantees will carry over as a result. So then, yeah, IPPO, which I'll talk about maybe a little bit more detail when I talk about MAPPO for the C2DE case. The standard version of IPPO, independent PPO, uses parameter sharing, which means that the agents use the same network for learning policies or values or both. So that to me is not DTE, is not decentralized, because you have to share the information, right? You need to share the parameters, you need to share the updates. So that's not decentralized. That would need to be done in a centralized phase. So then I consider that part of the CTDE case, but if you don't use parameter sharing, then that would qualify into the decentralized case. So yeah, the decentralized case is still not super active, but there are a bunch of methods for solving that, some of which I didn't talk about here. There's certainly many more papers in Marl that I can talk about in this time, but these are the basic ones for these two cases. I'll also say that, yeah, so then maybe I could talk about it later depending on how much time as well. So because of these convergence guarantees, it winds up that the CTDE case and the DTE case, the decentralized and the centralized training with decentralized execution case, aren't actually that different in a bunch of cases, even though people tend to like the CTDE case better. Yeah, I'll also say that other people call things decentralized. I mean decentralized how I talked about it in these slides, but there are decentralized from meaning networked, or these other types of decentralized multi-agent RL methods that are not included here. Okay, so then I was going to talk about, spend the rest of the time on the CTDE case, unless there's other questions in the meantime.
There's one question in the chat box.
Okay.
Okay, Solomon asked, so in the decentralized case, do we model the changes caused by the other agent as a part of our state representation to be able to perform individual learning? Can shared buffer technique handle non-stationarity caused by other agents with the same state representation?
So, yeah, so there's two questions there. One is there are methods, but there's more CTDE methods that do try to model the other agents' changes, right? So there's like work by Jacob Forrester, right, and other folks, right, on learning with opponent awareness, that kind of stuff, right, that does try to model some of the things that are happening, fingerprinting, other stuff, for directly learning about how, similar to what, where the equation way back here, if I can go that far. So this equation is obviously quite hard to learn. You need a lot of data, and data that you wouldn't have in the decentralized case in order to learn. But you can learn approximations of this, things that are enough to help you learn a little bit better. So there are methods for doing that. So that's my quick answer, at least, to the first question. For the second question, in terms of the buffers, right? So the buffers themselves, they make it more stable. They make learning more stable, but they don't by themselves guarantee or are not enough for convergence. So there's Q-based methods, because of the argmax, other issues, it makes it hard to guarantee convergence. So it's a bit more fiddly. It's a little unclear what, or at least from my perspective, there is work in that area, but it's not clear what assumptions you need in order to get. I think you would need, that would be one thing that's necessary, but it's not sufficient to have convergence, I think. Okay, so if there's not more questions, then I'll go on to the CTDE case. And but again, is there more questions?
No. Just I want to say thank you. There is no question.
Okay. So the CTDE case is the most common case, right? It's the case in which you assume that you have the centralized offline training phase, right? So then the assumption here is that each agent now observes their current observation, right? And then chooses an action at their history, right? Whatever the representation of their history is. then you have some centralized algorithm that gathers this information, right? That sees all the observations from all the agents, all the actions from all the agents, and the joint reward, and possibly other stuff like the underlying state that we'll talk about later on. And then uses that information, right, to try and help figure out what the agents should do, right? Gives them basically their policies at that point, right? And this is by far the most common type of cooperative model, right? And it makes sense. If we're cooperating and we're using a simulator, why not like try and simulate a bunch of stuff and say, like, what if I try this policy and you try that policy? How well does it do? Right. And let's change and see how well that does. Right. We can have this phase of coordinating, sharing information, right? Even though during execution, right, when we're actually in the world, we don't have that communication channel, right? We're not in the simulator, we're in the real world at that point. So then, yeah, so this is, we still want to execute in a decentralized manner. So then it's more scalable than a centralized case, but it can be less scalable than the fully decentralized case. And there's many methods. The vast majority of methods that you've probably heard of for the Marl case fall into this bucket of CTDE, right? MADPG, COMA, QMix, QPlex, MAPPO, etc. Which we can talk about them. Okay, so then first the action value methods, right? So these are the value function factorization or value function decomposition methods. The basic idea there is, so we want to do a queue-based method, but we need to be able to execute, right? So there's no policy model in these cases, right? In a value-based method, there's no policy model, so we just have queue functions. So in order to execute, each agent needs its own queue function. Right, so then we need to learn queue functions per agent, which is what we have on the bottom here. But then we want to use centralized information in order to learn, right? So we want to try and figure out some way of combining these queue functions per agent into some joint queue function, which we can use during training, right? To train those individual queue functions per agent. That's kind of the idea there. So we can imagine we're decomposing or factorizing this joint queue function into these local queue functions per agent. And there's just a bunch of different ways of doing this, basically. So in the simplest way of doing that is VDN, or value decomposition networks. So the idea there is basically you have like a DRQN network per agent. If you're using parameter sharing, then there's just one, right? That's used by all agents. But then otherwise, it's you have N DRQN networks, right? One per agent. And then the way of combining these local queue functions into the joint queue function is just summing them together, right? That's the simplest thing you could possibly think of, right? Is like we just take all of our queue functions, we sum them together to get our joint value. And then we can use the joint value to do RL loss on, just like you would in any queue-based method, right? So then you just calculate the target. And here, the nice part is you can calculate the target by argmaxing over each agent's local queue function. So you don't have to do an argmax over the joint queue function, right? You can just do a max over the local queue function. So it's not as, so it's more scalable that way. It keeps it scalable by just maxing over that smaller space rather than the joint space, which is exponential in the number of agents, right? So we can calculate the target that way, right? As it's just the joint Q value as the sum, and then we can use that target, right? That joint target to help us learn the individual Q values per agent. And that's basically it. There's pseudocode in the book, but I think I took it out of here for sake of time. But then using the sum is obviously pretty simple, right? And then we won't be able to represent all the Q functions that way, right? So there'll be lots of error in our learning as a result of that. We won't be able to get the Q functions that properly represent the joint Q function. So we can imagine more complex ways of combining these Q functions together in order to get the true joint Q function. So that's QMix is trying to do that by extending the idea. Instead of using sum, it's using monotonic functions, which are just more general than using sums. So then instead of just summing them together, it now has a mixing network with positive weights to make sure that the output is monotonic. It also uses this idea of saying, well, during training, we have access to other stuff in the simulator, such as the state of the underlying state of the world, the true state. We can shove that into the mixing network as well to help us learn. And then we learn this Q function that depends on the joint histories, the state, and the actions. And we can use all that information, right, to help us calculate these targets. And then again, we can just do this local argmaxing in order to put that value into the joint Q function in order to get the values. So this is this works surprisingly well. And yeah, it's a paper from 2018, but it's still one of the state-of-the-art methods, right? Still outperforms other methods on at least some domains. But then you can imagine more general case. So still, monotonic functions are not sufficient to represent all possible Q functions. So there'll still be, you won't be able to learn the correct Q functions in at least some cases there. So then there was this idea that came up of individual global max, or IGM. And the basic idea there is that you want to try and have a equality, right, between the argmaxes of the joint thing and the local thing, right? So if they're equivalent, right, if I can argmax over the local things and I get the same thing as I would if I just argmaxed over the joint thing, then I don't need to argmax over the joint thing. I can just argmax over the local things, right? So that's just recognized. It's the same thing that VDN and Qplex and Qmix rather, we're already satisfying that, right? That by using sums and monotonic functions, then the argmax of the local things would produce the same as the argmax over the joint thing. But we want to have more general functions where this holds for any Q function. So then that's the idea of other decomposition methods or factorization methods, such as Qtran and Qplex, that try and learn more general questions so that they can learn anything that is IGMable, right? Any case in which the argmax is the same, right? You want to be able to learn that function. So then Qplex is one such algorithm, and again, one of the state-of-the-art algorithms that extends that idea. It also does some different extensions. Like one kind of subtle trick there is it defines the advantage-based IGM case, where it uses a particular advantage where the value is assumed to be, it doesn't learn a separate value model and a separate Q model, right? Like dueling methods would do. Instead, it learns a Q model, and then it generates the value as the max of the Q model. So the V of H is just going to be the max of the Q, right? And that's for the joint case as well as for the local case. So use a particular form of advantage, but then using that particular form of advantage, now I can just define this advantage-based IGM, and it looks exactly the same as what we had in the previous slide, just replace the Q's with the A's and is. But there's a subtle thing of using this particular type of advantage, right? Where we use this advantage where we have this V is the max of the Q, it makes it so that it's 0 for the optimal action and negative otherwise. So it allows us to have this kind of implicit constraint that we can now put into our models to make sure that this holds, right? And then it makes us able to represent IGM by using this constraint as opposed to just picking particular functions like we did in the previous cases. And that makes the architecture a little bit more complicated, potentially a little bit more complicated than it needs to be. But otherwise, it's the same basic idea as what we had before. Again, just making like much more complicated mixing network. You can imagine like this whole thing is kind of a big mixing network. But you still have DRQNs for the agents generating individual Q functions because that's what you need for execution. But then those get decomposed right into the advantage and the value functions and then transformed, right, in order to try and get the final output at the end. I won't really go into it in too much detail because it probably would take some time. But again, I'm happy to answer questions as necessary. But it's worth pointing out that we just talked about that we could use the state in these cases. So is this using the state in these models cheating or wrong, right? Because you can imagine if we're using this information during training, maybe it's somehow being used during execution, right, where we don't have it, or maybe it's needed during execution where we don't have it, right? Maybe it's doing something to our policy that's making it wrong, biased, or something. And it turns out that there's a couple of different answers there. So it turns out that it's not wrong to use this state information. It doesn't bias your solution. You still can generate a solution that just depends on the histories, because you basically are just throwing all this stuff away and you're using these values. And then when you're calculating them, these individual values, you're basically marginalizing out the state information. So it's not wrong, but it does restrict Qplex by the particular implementation that they use, where you use the state. It makes it so that you can't represent all IGM functions anymore using the state. Technically, you would need to input the joint histories in order to be able to represent all IGM functions. But again, I can go into that more detail if people really want. But it's and it also turns out that that using the state may not even be the best thing to use there, right? We did some experiments checking other things, trying to figure out like why is the state useful, what may it contribute there. In some cases, the state does turn out to be the best, but in other cases, it turns out that if we just use some random number, right, or a constant, then that turns out to perform even better than using the state. So it's still a little bit unclear what the purpose of the state is there, or how to best do include other information or do CTDE more generally for these value function decomposition methods. But it's an interesting point. Okay, so then the policy gradient methods in the last time that we have. So now the main method for the policy gradient methods for the CTDE case is to assume that you have a centralized critic. So this is an example of that, right? So now we assume we have decentralized actors. So the decentralized actors are necessary because during execution, we have to assume that each agent can act on its own. So then during training, we can use this centralized critic. But then during execution, we throw away the centralized critic, and each agent just keeps its policy model, and then can just execute based on its policy model, right? It just inputs observations, and then the policy model outputs actions that it should take, right? It can do this. So then the idea is to learn the centralized Q function during training, and use that centralized Q function to help learn these decentralized actors. That's the basic idea there. So yeah, I don't have time to go through this in too much detail. This is basically a version of independent actor as with a centralized critic case. So it's basically this decentralized actor and centralized critic in that case, right? Using joint policy model, right, or joint value model rather, and then updating those to learn these independent policies, decentralized policies. So, so maybe jump to the first two algorithms, really. MADDPD and COMA popularized this idea of using centralized critics. And originally, yeah, MADDPG was designed for competitive or cooperative problems. It's off policy, yeah, so it uses a replay buffer. It's continuous action, so yeah, our the updates are going to look a little bit different here because we're using deterministic policy gradient. And then, yeah, the original methods just defined it based on a single observation. But then again, that only works in cases in which the problem's not really parse-observable, if you don't need to remember stuff in the past. So I'm writing it out using full histories here because you may need to remember stuff in the past is more general. And then the basic idea is, again, now combining some of these ideas that we saw for the DQN case using a target network, right, with some of the ideas from the policy gradient case. We have this centralized critic, and the centralized critic takes in the joint histories and actions of all the agents, right, learns that value, right, and then updates the individual actors of the agents. And MADDPG started this idea along with COMA of using a centralized critic. That basic idea of using a centralized critic is still widely used, but MADDPG itself is not super widely used. COMA, like I said, right, is the other algorithm for doing this, but it also introduces this counterfactual baseline to help with credit assignment, right? Thinking that, you know, in the multi-agent case, especially the cooperative multi-agent case, you get a joint reward, but what agent did something useful there, and what did they do that was useful? So the idea there is to try and use this advantage calculation, which subtracts off, right, like the expected thing, right? So this is the difference between what you did, right, and the expected thing from your policy, and then fixing the actions of the other agents, right? So then looking at the contribution of the action that you actually took versus the, you know, what you would normally do, right, to try and help with credit assignment, and incorporating that as the joint critic, right, using that per agent. And then otherwise, yeah, doing the update in a similar kind of way as what we saw before. And COMA is, again, not super widely used anymore, but very influential as a result of this idea. So what is widely used is MAPPO, but it's basically just taking the ideas that we had in the MADPG and COMA, right? It's just using and replacing the particular underlying method, right? For all these methods that we talked about, you can just take ideas, right, particular algorithms from the single agent case and apply them in the way that the framework, like the centralized critic kind of way, right, using using PPO rather as the base RL method. Right, so you can do that for any particular. You could use TRPO, you can use SAC, you can use whatever. You're just adapting it for the particular cases that you're interested in here, right? So then there, like we just use the particular appropriate losses, right? The particular algorithm. So we use the PPO clip loss, right, for the actor, which is here, right? And then in the multi-agent PPO case, then it uses this joint advantage, which yeah, they use GAE, but it doesn't. You can use other calculations for calculating the value function. And then using the policy ratio, right? So where now this is the ratio for a particular agent, right? So again, taking the particular actions and that agent's history. In their case, they also use a clipped loss, right, for the critic. You can use a clip. Sometimes it performs better to not use a clip loss. Sometimes it performs better to use a clip loss. It's written here because that's what they do in the paper. And yeah, so like before, we can use other information, other centralized information in the critic as well, use state and other thing. The basic, and so this basic idea, right, MAPPO, the algorithm, it works surprisingly well. I guess like PPO in general works surprisingly well, right? And again, this is a few years old at this point, MAPPO, but still one of, if not the state of the art in many different domains that exist. Some form of MAPPO often performs best. And IPPO, just to make it clear, right, is basically the same as what we would do for MAPPO. It just changes the advantage calculation. So instead of calculating a joint advantage, then you have a local advantage, right? So this is the advantage. You have a local V model per agent, right? And then you calculate the advantage based on that, right, for each agent's advantage. And then you replace the joint advantage with the local advantage in the update, right, which is what we have here. We have AI versus in the MAPPO case, it's the joint A, right? That's the difference there. Same thing. So the critic, again, the clipping, right? And now we just have this per agent value function. Yeah, and IPPO often performs similarly, sometimes lower performance than MAPPO. So I don't have a lot of time left. So I think maybe I'll super quickly mention some of this stuff, and then I'm happy to talk more about anything else that people want to talk about. Are there questions so far, though? Should I stop here and take questions, or people want me to keep going?
There's no question from the audience, but we have about half an hour left. I think there's no rush. We can cover
Okay.
anything in it. Yeah.
All right. So then, so then I'll talk about this stuff, but try and leave time for questions at the end. Like I said before, there's a bunch of similarities between the decentralized case and the centralized CTDE case, not the fully centralized case. So then when MADDPG and COMA came out, people just started using centralized critics and just assumed using centralized critics was always the better thing to do because they somehow foster cooperation, right, or help improve performance over the decentralized critic case. It turns out that that's actually not true. It turns out that they both, in theory, are the same, right? They both estimate, which is exactly what you want, right? So they both estimate your decentralized actors, right? The whole point of a critic is to just tell you how good your decentralized actors are, to evaluate your decentralized actors, right? So then both cases, the decentralized case and the centralized case, are just evaluating the decentralized actors. So they're not, the centralized case isn't wrong, right? It is calculating the correct value in general for the, we can talk about some caveats in a second, for the decentralized actors, but it's not calculating a different value than the decentralized case. So it doesn't help in theory. In practice, it matters because the theory assumes that the critics are converged and are correct, but it may be harder to learn a centralized critic in some cases and harder to learn decentralized critics in other cases. And that causes this kind of bias variance trade-off. So where sometimes it may make more sense to use a decentralized critic and sometimes to use a centralized critic. And as I'll talk about later on, there's an added benefit of using the centralized critic in the sense that now I can add this other information, again, whether it's a state, whether it's some random number, whether it's a constant, whether it's other junk, right? Then that may also be able to improve performance. But first, for the without using state or other stuff, I won't go into this in detail. This is talking about, again, like what we saw on the slides before. In the decentralized case, we just calculate each agent kind of separately, right? But we assume that there's kind of concurrent learning. So all the agents are learning at the same time from the same data. And then in the centralized case, then we have what we did in the other algorithms, right? Which is basically, so now we just calculate the joint Q value, and then we use that joint Q value to update each of the individual agents' actors. And what turns out in those cases, it's really just a matter of kind of when, in order to update the decentralized actors, at some point you need to marginalize out the information from the other agents, right? So I can't use that other information. I can't use your actions, right, in my policy update, right? So I have to just make my update on my own, right, to update my decentralized actor. So then in the decentralized critic case, as you can imagine, right, so then when my Q calculation, I'm marginalizing out all the other agents. Like we had in the equations before, assuming it's just a POMDP with some fixed other agents is really what's kind of happening in the Q model there. So it's just marginalizing out all the other agents, right? Or what's happening with the other agents. So then I already marginalized that out when I got to the Q function, and then I just use that for the actor. But in the centralized critic case, the marginalization just happens later, right? I calculate the joint Q function, but then when I'm calculating the update, I just sample from the actions of the other agents, for instance, right? And the observations, right? In order to try and marginalize out the other agents. And then the sample frequency comes from the buffers or whatever my algorithm is. So then it's basically it's just empirical distribution of what we had before anyway. So it's marginalizing out the information one way or the other. It's just like basically where the expectation comes from and what the expectation is over. It's just broken up in different ways for the centralized case or the decentralized case. Which again is exactly what you want, because then it proves that the critic converges to the right thing, right? Like in both cases, you can now prove that the critic would converge to the right thing, right? The correct value function for the decentralized actors. And that is exactly what you want in those cases. It just means that it doesn't help with learning any better in that case. And it actually turns out that that's true for experiments as well. We tested that on a bunch of different domains, and it turns out that mostly they're the same. There are some cases in which the decentralized works better, and some cases with the centralized works better, such as that case that the centralized doesn't work as well as the decentralized case. Cases in which there's variance could cause an issue usually in learning, for instance. And so it turns out that they're theoretically equivalent, and then but decentralized critics can be harder to learn when there's a lot of non-stationarity. So then, like, if the other agents change their policies a lot, right, then my Q model gets stale, right, because I have a Q model over only my stuff, right? So then that kind of underlying POMDP changes a lot, and therefore my Q model is no longer correct. So then I'm gonna now update my actor in the wrong way. So then that could have a higher bias because the Q model can be wrong in that case. Whereas the centralized critic can sometimes be harder to learn, like in particular large domains, right? Because I have to learn over this joint space. It may also be higher variance to marginalize out the other agents, like I said before. So then I may have a higher variance update of my actors as a result of that. And that could cause instability in the learning and poor performance. So unfortunately, you kind of have to think about your particular domain and which one makes sense, whether you should use decentralized critics or centralized critics as a result. And then, as I said, it's also become quite popular to use some sort of state information in the critics. And before, for the value function factorization case, we had both the history and the state in there. But some of the methods, particularly MAD, PG, and to some extent COMA, as well as a bunch of other methods, and you even still see this in papers today, use just a purely state-based critic. So where the problem itself is parse observable, so the actors are using histories, but the critic is only using the state and the joint action. And that seems like a good idea, because it's like, why learn history representation, right? Like, why learn what the important thing is in the history to remember when you already have the state? Just use the state anyway, then you can get rid of all that parse observability. And that's kind of the intuition there. But it turns out that it's wrong. So actually, it turns out that purely state-based critics are just incorrect, and they only work in cases that the problem is very often close to fully observable, or too difficult, right, to bother remember anything in the past. There's a bunch of kind of corner cases in which it could potentially work well, and the only reason why people thought it worked well is because it worked well in SMAC, right, StarCraft environments that were basically fully observable, or simple to solve from that information. So then so in theory, they may be biased, which means they may be wrong. They may calculate the wrong value compared to the history-based critics, which are the correct thing. They also may produce higher variance, which isn't particularly helpful. And then, like in the value function factorization case, using the state and the history, that is a valid thing that's both correct and can perform well. So that turns out to be usually the thing that you would want to pick. So then I'll talk about that very briefly, kind of a little bit more detail. But again, if people have questions, I can talk about it more. So a little bit more clearly, right? So then the history-based critic, right, takes in the history, the centralized history-based critic takes in the joint history, right, and joint action, right, and produces a Q value. The state-based critic only takes in the state of the world and the joint action and produces the Q value. In all these cases, again, we assume that we're in a parse observable problem, so the actors take histories in to choose actions. The history state critic takes the history and the current state and the joint action, right, and produces the Q value. All of them, update the history-based decentralized actors. So then this is a set of experiments very quickly, talking about some of these things, testing out some of these different methods. And in a bunch of cases, they work about the same, but in other cases, the history and state critic tends to perform the best. And then, so StarCraft, right? So this is the case in which the state-based critic does perform better. And again, that's because for the history case, you have to learn what to remember and what to forget. And if you're just giving basically like the same information over and over again, the recurrent model has to learn to ignore stuff. But if the state is basically the same as like a single observation, right, then you have the information already. You don't need to learn what to remember, what to forget. So then you can also just use either a single observation or the state, and that will tend to perform fine. As you add more parse observability, then the models that just use the state just tend to perform worse. The models that just perform just depend on a single observation to perform worse. Right, that's what's going on here. So then that kind of leads to the point that, it kind of exposes that we had some bad domains. And that's one of the reasons why we didn't notice this earlier. And I think that is something that people are working on. They're coming up with much more parse observable and more interesting domains. But in general, if you want to try and pick a method to use, using centralized critics is fine. Using decentralized critics is fine. If you use a centralized critic, you should use either a state and history-based critic or just a purely history-based critic. The MAPPO paper also found a similar result, where they wound up, the thing that worked the best was kind of a handcrafted version of the features from the state and the observations, the history that could work the best. It's still not completely clear why the state history critic, or how to best use the state information during training, but it's a good open question to look at. And it's an open question as to like what the best way is to perform CTDE more generally, in a way that actually, is theoretically correct, but also can perform well in lots of domains. And I'll point out that using the state and the history in the critics is something that is simple to do, right? It's just additional information. The state is usually relatively compact, easy to pass into things as well, and then can perform well. So that is one case of that is both principled and performs well, the state history critic. So there's many other methods. So in the book, right, we have the book draft as well as the older version of the book. There's a bunch of other details about things. There's many extensions that people have made combining factorization with policy gradient methods. For instance, parameter sharing, like I talked about before, is extremely common, right? Some form of parameter sharing with agent IDs or without agent IDs, right, for various types of problems. Extending it to heterogeneous agents, all this kind of stuff, right? So in general, that can perform well. I didn't talk about a bunch of other methods that exist. Like there's methods that do alternated learning where agents update or choose actions one at a time, right? Or do full learning until convergence, right? And then swap and the next agent learns and the next agent learns. So there's a bunch of other kind of cases that also fit within CDDE, but the two main methods are these factorization methods or decomposition methods and the centralized critic methods. Like I sort of talked about before, there's other kind of agent modeling cases that also fit in this CTDE bucket. Right? It's a very big bucket with lots of different methods that I didn't really have time to talk about in detail. There's also many other topics in moral and in cooperative moral, more generally, that I didn't talk about at all here because I didn't have time. Right, like communication is a huge topic. Like who should the agents communicate to? What should they send? Right, when should they send it? It's a huge question in moral more generally. This is a particular survey paper. I can share these slides with these links if it's helpful. Ad hoc teamwork is a very common problem as well. That's another survey for that case, right, where agents could come and go, right? So you don't know which particular team you're going to be interacting with, right? So you have to try and learn or plan or solve the problem where you need to do well with the particular agents that come to solve the problem with you. There's lots of model-based methods that are trying to be used now in the moral case too. So there's a survey paper on that, right? Learning the model, which can be difficult in the multi-agent case, right? Because the model becomes much more complicated, as well as like the general problems that exist here, right? So it's just exploration, offline methods. I guess I already have model-based methods there. Hierarchical methods, role decomposition, multitask, et cetera, et cetera. There's a plethora of methods that exist that I didn't have time to talk about here. That hopefully we're going to include in the full book when we have that. But I can talk about it to some degree if people have questions. Application. So this is becoming a topic now where people are starting to try to apply multi-agent stuff in various scenarios. One example that I talked about before already was the alpha star case, right? Which is maybe not a full application, right? But it is like performing very well at a video game. And you can imagine, because a lot of the benchmarks in RL are based on video games, you can imagine that that's a very simple kind of thing to do because you have that simulator already available to you, right? And you can use that directly. And that was a case of centralized moral for the team there. And then playing against the opponents, right? Sampling using population-based methods, if I remember, for the opponents. And then, but you also have people trying to use moral in various applications, such as warehouse robotics, right? So that you have a team of these robots and you're trying to coordinate them. So there's, for instance, this particular method uses a hierarchical approach that's CTDE for trying to coordinate the robots, right, in a scalable manner, so you can still execute them in a relatively local fashion and solve this warehouse task. That's this image, the second image here. Things like traffic control are widely studied now in the moral literature. Trying to apply these moral approaches to controlling traffic lights, right? When you should change the light from yellow to red to green, etc. There's lots of different methods that try to solve these problems. These have particular factorization methods that could work there because of how the networks are kind of arranged in those cases, because those agents are not moving, right? They're stationary and they're related to the traffic flows. So there's papers on various moral methods there. Yeah, autonomous cars, right? So having fleets of autonomous cars, that's a cooperative problem. If it's not your own autonomous cars, then it becomes a mixed or potentially competitive problem. There's survey paper there. I can send links to this stuff, although I guess it's in the paper draft, the book draft. But there's a bunch of other applications, power systems, et cetera, that people are trying to now are excited about trying to use Marl on. So we'll see what happens in those cases. This is one of my examples from my lab where it's like a small kind of scenario where we have people building furniture here. This is IKEA furniture, and they have small robots that need to learn when to bring the proper tools to the people at the right time to not interrupt their workflow, but make sure that they have what they need when they need it. So they need to learn who to go to when and what to bring them. And the fetch robot, so the one with the arm, needs to figure out what to give the particular smaller robots at the right time as well. So then they had to learn this completely on their own, right, as to what to do based on interacting with the people in this case, right? So that's the basic, that's a kind of simple scenario for thinking about there. And in terms of benchmarks, so then there's lots of benchmarks and they're growing. So the standard ones that people use still are like the particle environments, which is the one on the top here, which is available in PyTorch and JAX. Overcooked, which is also available in PyTorch and JAX, which is represented here, which is based on the video game where you have to cook stuff, you have to chop some things, put the other ingredients, put it on a plate, deliver stuff. And they get more complicated in terms of the arrangement and what the different agents have to do and coordinate on in order to solve the problem. And then there's extensions of SMAC, so the StarCraft multi-agent challenge, right? So then I said before that the original version, which is V1, was not very parse observable, so people have extended that, or I guess the group in Oxford has extended that to more parse observable settings and more difficult settings because they were becoming saturated. They're like the MPE ones are also pretty saturated, where methods can perform very well at them. So then we needed harder domains in order to be able to solve them. And there's many others that are coming out constantly in terms of the domains. We kind of, as a community, need to try and decide which ones we want to pick, right? There's so many domains that exist out there. Which ones do we want to pick as like the standard benchmarks for the community? And there's lots of opportunities to download code and to play with stuff. You can look at a bunch of the environments in Petting Zoo, for instance. JAX Marl is a nice set of methods and environments that exist in JAX. So it makes it more efficient so that you can run many more experiments, right, in these domains, right, which can take a long time to run experiments in. So then JAX can be much more efficient, although maybe your code is harder to write in JAX. And then as well as other things like BenchMarl, which is PyTorch based, right, that has methods, environments, etc. So those are some of the common ones that people can look at if you want to play with this stuff more. And then I feel like I have to have a slide on LLMs nowadays. And I'll say, like, so I was last week, 2 weeks ago, I was looking at like what's the status of Marl and LLMs in general. And so I'm working on this to some degree, but not super widely. People are trying to do things with Marl or multi-agents and LLMs very generally, but there's and certainly like single agent RL is used to train LLMs, but there's not much. There's starting to be a little bit of work on training LLMs using Marl to get them to cooperate, compete, whatever, right? Kind of thing. But it's very at its infancy now. But there's no reason why it couldn't work well. Why you couldn't just take any of the things that I talked about before, at least in concept, right? In practice, it's quite hard, I think. But like in theory, LLMs are just agents kind of by themselves, right? So then it's just an agent architecture. So you could potentially use some form of Marl to train them. But there's lots of open questions there in terms of what are the right use cases for this, right? Like nowadays, like this picture at the top, right? So these are pictures from NVIDIA and Microsoft here. Lots of companies and people more generally are trying to use multi-agent stuff to solve the problems, but having a hard time just trying to find like what makes sense. Like, when does it make sense to use multi-agent? When does it not make sense to use multi-agent? And this case from NVIDIA is just a bunch of coding agents that potentially, like, maybe you have a lot of coding agents, they work together to generate this like whole code base that you need to write your application, right, or your video game or whatever it is. So some of these may make sense to using multi-agent in, some of them may not. Maybe you just use some form of single agent kind of approach, right? So then the benefits in general of using multi-agent, like traditionally, is it allows you to specialize, right? You can have different agents that are experts at different things, right, or good at different things, so that you don't have to have general agents for all the things, right? You can allow agents to specialize in different things, like maybe, this agent writes particular type of code, right, or is a code writing agent, and other agents are other types of agents. You can allow them to specialize in their particular field. Also allows robustness, right? So that by having multiple agents, right, certain agents could fail, certain agents won't do as well, right? So you can use the other agents to try and improve the performance that you would get. Similarly, scalability and performance, right? So scalability, right, by breaking up the problem into a bunch of different problems, right, that each of the agents can solve and then combine their solution, we could potentially scale to much larger problems than we could otherwise. And that could also allow better performance, because we wouldn't be able to solve it very well with this like one big agent. Maybe we can solve it much better to improve performance with a bunch of smaller agents. But yeah, so then the use cases and then the control scheme. So is it a centralized problem? Is it a decentralized problem? Is it a CTDE problem? What is it? And then RLHF is widely studied, although I would argue, I think there's still a lot of room for improvement there. But what about MARL HF? Like, what about multi-agent RLHF? Like, that's I think there's one paper that I saw on that. Maybe there's more. How do you train these things, right? Like, training is obviously difficult in the single agent case even. So what are the right ways of doing this for the multi-agent case? I think there's a lot of open questions on how to use MARL to help train LLMs, right? There are methods that try to use LLMs to help MARL, right, just out of the box, right, with prompting and other things, or dialogue or this other stuff. But directly training with MARL is a very much open question, I think. Well, more generally, MARL and LLMs is an open question. And then I think there's a big disconnect between academia and industry in these cases, where industry is trying lots of stuff, which is great, right? And I think, in academia is developing algorithms for things. I think we need to talk more to try and make sure that the stuff that that they don't reinvent the wheel, and that we invent stuff that's useful for them. So I think that should probably happen at some point too. So with that, maybe I'll conclude and say that with a couple of slides here, the cooperative MARL is a very general setting with lots of applications. There's lots of work on cooperative MARL. I talked about the centralized case, the decentralized case, the CTDE case, and there's lots of a very active community in both academia and industry working on these problems. And there's many open questions for people that want to work in this area. Lots of people want to do things for LLMs nowadays. And it's this question of what's the right way to use them more generally in these kind of multi-agent scenarios. How do we have like super scalable MARL so that we can like train from massive data sets to solve these massive problems? It's related to the problem of the mean field case. That's also a massive kind of problem. Yeah, how do we get optimal? Like, how do we get guarantees? Can we say anything theoretically about any of this stuff, or is it just like purely empirical? How to best do CTE? Like, what's the best way? Like, what information do we use? How do we share it with the agents? How do we use it for updates to best use the information that we have in the centralized phase? And then like multi-agent approaches to machine learning more generally. How do we use these ideas and apply them to these other settings? Decentralized methods, GANs, et cetera, could also be applied, from the multi-agent perspective. And I'll end with some resources, right? So we have the book. I guess I didn't put a link to the, no, I didn't. I didn't put a link to the book, but a book looks like that for the book that we wrote a few years ago, I don't know, 10 years ago, maybe now, on DEC-DP is giving just background on like the model and some planning methods. We're working on a book now to talk about learning methods, right? And there's a draft of the book there. There's slides some version of these slides, just slightly longer, but a very similar version of these slides is available at that website. Franz's slides, as well as my slides related to that. If people want to take a look. If people have any comments about any of the resources that are available there or questions about it, then I'm more than happy to answer, as well as any questions that people have for here today. And I think that's the end of these slides. Oh, I only have a couple minutes left anyway. So hopefully I can answer questions if there's questions here at the end.
Thank you very much, Professor, for a great presentation. I'm so excited about the whole thing that we talked, and honestly, there's a lot to take in. I'm still trying.
Yeah.
There's a lot. So let's see if the audience has a question. We have only 2 minutes. If you have a question, please raise your hand. I don't see anyone raising their hand. So, because in the sake of time, just for the closing question, I want to ask, what's your advice for the students who wants to start their research career in the reinforcement learning or multi-agent reinforcement learning, and to find something interesting to work on and go on and do something interesting? What's your advice for them?
Yeah, that's a great question, because I feel like I talk to a lot of people that have tried something. Like nowadays, people are trying to do something with like LLMs and multi-agent stuff, and it's very easy to kind of fail there, and it's very hard to get something working well there. So maybe the suggestion is to start with things that kind of already exist. I think you want to just start by understanding stuff. I that's how I like to start, at least. So then environments and code. I would start by just trying to get stuff working in common environments, trying to understand the current code in like reproduce results of in these current environments, right? And then try to do some of these more simple things. Like, for instance, this issue related to like states and other information in CTDE. It would be easy to try and see what happens in different environments, right? Or you could try like there was a cool paper that I saw the other day where it was just trying current methods in environments that they weren't trained for, right? Either directly applying them or training them on those environments and seeing how well they did, and then trying to figure out like why did it work well there? Did it not work well there? Right? Like those are things that are easy and kind of low hanging fruit, just to get like a better sense of what the methods are. People just get so excited and they want to work on like the next like super cool thing. But it's hard to work on like that. Like you got to start somewhere. I would just back off a little bit, try to understand things a little bit better, feel more comfortable about it, and then work on the next big thing. You could still work on the next big thing. Just like wait a little bit before you get there.
Yeah, that's a great advice, Professor. And I think our time is up. And with that, I want to thank you again for accepting our invite and giving us this awesome presentation with all of this excitement. Thank you.
Yeah, no problem. Again, the resources are available. If anybody has questions or comments or anything, feel free to let me know.
Sure. Thank you, and have a good rest of the day.
Thanks, you too.
Bye.